So in the last video we have this SIP methods. So this is the principle of inclusion exclusion. So we establish this result. Okay, so this is the procedure. It is written in this systematic way. Okay, so this is principle of inclusion exclusion. So now we are going to proceed for our next discussion. So we'll find out the compact form of this principle of inclusion exclusion. Okay, so whenever we're going to write down a set, actually a set is represented in two ways. One is actually tabular form, or other is actually set builder form. Okay, so that is set builder form means the elements of the set satisfy certain property. Satisfy certain property. So we need that concept to proceed our next discussion, So say you consider these are the properties with the set of properties that the elements of the set X may or may not possess. Okay, we consider these n properties. Okay, the elements of the set capital X, that is the universal set here, capital X, may or may not possess. So say E1, the elements of A1 satisfy E1, element of A2 satisfy E2, okay, element of AN satisfy EN, something like that. Properties EI, and satisfy element of AI satisfy EI means the element of AI may satisfy more than EI. Actually, it satisfies EI and it may satisfy E2, E3, E4, something like that. But it satisfies actually the property EI. It is true. So then what does it imply? This implies is the number of elements which don't satisfy one of these properties. Okay, that is, if I consider X difference this, that is, if I count this number of elements, X difference this, union of I from 1 to n. Okay, so that is, we are actually deleting all the elements which satisfies the properties E1, E2, En. Okay, E1, E2, En. Okay, so that is this set represents the number of elements that possesses none of the properties. Okay, none of the properties. So then AI1 intersection AIT is up to this. This is the set which contains actually these T properties. Okay, EI1, EI2 up to EIT. Okay, these T properties intersection. If I consider A1 intersection A2 intersection AN, that is this intersection satisfy all those n properties E1, E2 up to En. Okay, and maybe others. Okay, maybe other property intersection, because intersection may contains common element and more other elements will be there, maybe there. Okay, so now you see, now next representation we have this notation. We need this notation. So what is this notation actually? So this notation, this is the notation. There is a number of elements in the set capital X. This notation, something like that, superset of T, something like that. Okay, so X possesses at least the properties of T, Okay, if T is equal to say E1, that is X possesses at least the properties of T, that is at least the property E1. Okay, that is T is equal to E1. T contains the element E1. That is, this is nothing but actually, this is nothing but, if I consider T is equal to say, here you can write down, if T is equal to E1, so this is nothing but actually this expression, T is equal to E1. This is in our discussion, this is nothing but number of elements in the set A1. Okay, number of elements in the set A1. So this representation implies number of elements in the set capital X which satisfies the properties E1, maybe other properties. So okay, therefore this is nothing but actually number of elements in the set A1. Similarly, if I consider say this is if T is equal to say E1 comma E2, then this representation is nothing but, what does it imply? So number of elements in the set actually A1 intersection A2, something like that. Okay, something like that. So this is the representation. And if I consider this equality, okay, this equality, then what does it imply? It implies that X possesses precisely the properties in T. Okay, X possesses precisely the properties. How many properties are? If T contains only one property, okay, then X possesses only that property. Okay, X does not satisfy other properties. Okay, so that is the equality. So now in our principle of inclusion and exclusion, you can observe, okay, this principle of inclusion exclusion, this is the actually our principle of inclusion exclusion. Okay, so these are the notation we are using. Okay, so T is equal to E1 means this is something like that, E2 means something like that. Okay, T is equal to E2, this is number of element in A2. Okay, so that is this summation sign. Okay, this summation sign is nothing but T is equal to N in this this summation sign, this is something like that. Okay, so so if I consider this is E1 E2, T is equal to E1 E2, so we have this number of element in E1. Okay, number of element E1 E2, that is this. So this may be E1 say E3, E1 E3. Okay, E1 E3, so this can be written as something like that, E1 intersection A3, all those possible cases. Okay, all those possible cases. So this is the representation, that is this summation sign represents the this summation sign, that is this summation sign represents the elements of the form. You can write down this summation sign as this. Okay, where T contains exactly one element. Okay, then similarly this summation sign can be written is equal to this, where T contains exactly two elements, something like that, exactly 3 elements, 4 elements, something like that. Okay, so in terms, so mod of X, so mod of X means, so here you can see this is nothing but actually this can be written as this is equal to something like that. This is if T is equal to 5, if T is equal to 5, then what does it imply? What does it imply? What does it imply? It implies that at least the properties in phi, but there is no properties in phi. That is, it satisfies all the properties and number of elements which satisfies all the which satisfy either E1 or E2 or E3, something like that, or it does not satisfy any one of these properties. Okay, therefore this representation is nothing but this is equal to number of element in X. Okay, this is verified. Okay, so it satisfies at least the properties in phi, but phi does not contain any property. Okay, that is the set contains those elements which does not satisfy any properties of E1 E2 up to En, and but at least means it satisfies no properties, it satisfies one property, it satisfies two property, three property, four property, something like that. So this is the corresponding representation. So this expression can be written in the compact form. This is the compact form actually. Okay, that and you observe this part is nothing but you have to delete the elements which satisfies all satisfies the properties. That is, this part is nothing but all the elements which does not satisfy, all the elements which don't satisfy any one of this A1 A2 up to E1 E2 up to En. Okay, so that is, therefore this can be written as this is equal to phi actually. Okay, phi exactly the properties in T, but here phi is equal to T is equal to phi, that is exactly in the properties in phi, but there is no properties in phi. Okay, so no properties in phi means we are going to count the element of this set in the left hand side. Okay, so this can be written in this way. So in compact form actually, so you can write down this expression in this way. This is the corresponding compact form. So here starting from, okay, so depend t, what is t is nothing but how many properties we are going to consider. Okay, out of this n properties, how many properties we are going to consider. So if I consider number of properties in t is equal to 0, then you will get this part, you will get this part. Okay, number of properties t is equal to 0, then you will get this part. Okay, t is equal to 1 means this part, t is equal to 2 means this part, something like that. Okay, so depending upon whether it is plus minus, depending upon the value of number of element in t. Okay, so this can be written in the summation form. This expression can be written in the summation form. This is something like that. So this can be written in this way. Okay, so you are going to consider this is in general this is t, but t can take any value up to 0 to up to n. Okay, t can take number of element. Okay, that is number of element in t may be from 0 to n, because t is a subset. T is a subset of p. Okay, t is a subset of p. All those possible subset you have to consider. So you can write down this summation sign in this way, in this form. Okay, so summation sign varies in t. What is t? What is that? That is number of element in t is equal to k. Okay, so you just count count this set and take the sum. Okay, depending on minus 1 to the power. This will be remain same. So this is a generalized version of principle of inclusion exclusion. Okay, so if the number of element in t is equal to k, then this representation can be written in this way, and we call E as a set of homogeneous homogeneous properties actually. Okay, homogeneous set of properties or set of homogeneous property, same thing, same type of actually properties are there in t. Then we are going to use this notation. So you can see then in this case this is phi is nothing but this is equal to phi is equal to, what is phi? So phi does not contain any element. So what is phi? This will be 0 actually, but it is not. This will be 0, the left hand side. This may be 0. Yes, this is 0 actually. Okay, this is 0 in this case, and t. Okay, in this case you can see, in this case we are going to write down this is equal to k, t is equal to k, and depends on the cardinality, also depends on the cardinality of t. Thus for the homogeneous property we have this part. So this expression can be written as this is n is equal to 0, k from 0 to minus 1 to the power k. But here you can observe this summation sign is nothing but n choose k, n is greater than equal to k. So this summation sign means if I consider k is equal to 0, this will give the actually first part, but k is equal to 1. K is equal to 1 means actually this is a1, number of element in a1 plus a2 plus a3, something like that up to an. So this is nothing but in our previous discussion, this is nothing but n choose 1. Similarly for a1 intersection a2. Okay, for the second summation sign, for this summation sign, this is nothing but actually n choose 2. Okay, how many possibilities are there? This type of how many possibilities are there? How many possibilities are ai intersection aj? Okay, so out of this n element n set, how many possibilities are there? Yes, there are actually n choose 2 ways. Similarly, how many possibilities are there? A1 intersection ai intersection aj intersection ak, out of n set. So this is nothing but nc 3 ways. So this summation sign, last class we have already discussed this notation. Okay, last video also we have this part. Okay, so this summation sign can be written as in this way, So this is this is the formula in case of homogeneous property. It is same type of property, homogeneous property. So we are basically interested in homogeneous property. So here just to consider the one example. Okay, so see the example, quite interesting. So example is phi n. This is phi n. What is the phi n? You have to find out the d, such that d lies between 1 and n, and GCD of dn equal to 1. That is how many divisors are how many numbers are there which are relatively prime to n. Okay, relatively prime to n, phi n. Okay, number of, this is the relatively prime to n. So we can have it, we can derive the formula. Okay, phi n, you just remember from Euler's phi function. This is phi n means which are number of elements which are relatively prime to n and which are less than equal to n. Okay, so for this you just consider, suppose n is of the form, because this is the prime decomposition, prime factorization of n. Okay, by fundamental principle of fundamental principle of arithmetic. So we have this, you can write down n as a product of primes. Okay, up to t primes are there, and you consider let x equal to the set contains n elements. Okay, x is the set contains this n elements, and ei is the property. What is the property? That pi divides d. Okay, that is ai. In our previous discussion, what is ai? Ai is collection of all those elements. Ai is the collection of all those elements d in capital X such that pi divides d. Okay, pi divides d. Okay, so these are our a1, a2, a3, a4. Okay, now n equal to phi, that is the left hand side, n equal to phi. N equal to phi means, n equal to phi, what does it imply? N equal to phi means, okay, and phi is a subset of these properties of e1, e2. Okay, e1, e2 up to et. Here et properties are there. We are interested in t properties here. First property is e1 property is nothing but p1 divides d. Second property p2 divides d. So here are t primes are there, but therefore pt divides d. So n is equal to phi means n equal to phi. So this is actually number of elements which satisfies the properties in phi, but there is no property in phi. There is no properties in phi means, okay, there is no properties in phi means number of element which does not divide p1, which does not divide number of elements, that is number of elements which does not divide p1, number of element does not divide p2, number of element does not divide pt. So what does it imply? So this is nothing but the numbers which are relatively prime to n. Okay, this relatively prime to n, therefore this expression is equal to phi n. Okay, and next part, what is this expression? And this, the count, so you just observe this. What is this? The d, okay, d, you just consider d divides p1. If I consider t is equal to e1, that is the t contains e, t is nothing but e1, that is e1 is nothing but what is e1? E1 is nothing but p1 divides d. So p1 divides d. So d set is p1 divides d. Okay, p1 divides d. This is actually p1 divides d. Okay, p1 divides, that is d can be written as multiple of p1, something like that. D can be written as multiple of p1, x p1. Okay, x p1. So this expression actually, this is for only t is equal to e1 or t is equal to maybe e2, e3, e4, but t is equal to e1, e2. Okay, so in this case this will be actually all those the number of elements we are going to count the set. If I consider this is e1 comma e2, then we are going to count the elements such that this is multiple of p1, p2. The elements are multiple of p1, p2. So in general you can say that counts the integer less than equal to small n, this is not capital N, small n, that are multiples of, okay, that are multiples of this pi. Okay, ei belongs to d. Okay, that are multiples of pi. Okay, depending upon ei. Okay, depending upon ei. So now our objective is to find out what is this set. Our objective is to find out this set. So this is the, we are going to find out how many elements are there actually. Okay, which are less than n and multiple of this. Okay, so in general, say we have 10. Okay, how many elements are there which are multiple of 2? If you ask this question, okay, this question 10 is given, how many elements are there which are multiple of 2? Okay, so for this we are going to, what we are going to do, we are going to, how many elements are there? This will be 5. Okay, 5, something like that, because 2, 4, 6, okay, 8, 10, these are the elements. Similarly, how many elements are there which are multiple of, say, 5? This is nothing but 2, something like that. Okay, so here also, when we are going to this set, the elements of this set of the form something like that, that are multiple of this. So multiple of this means we are going to find out the number of elements, okay, of this set, number of elements. So this is nothing but n divided by this, n divided by this. So now we apply the formula, that is this formula. So what is the formula? So if I apply this formula, okay, this formula, so if I apply this formula, you can see put the value n is equal to, k is equal to 0 to n, okay, k is equal to 0, k is equal to 0. So k is equal to 0 means k is equal to 0, k is equal to 0 means it is pi, t is equal to, t is pi. Okay, so this representation is nothing but satisfies the elements which are relatively prime to n and which are not relatively prime to n. That is, this is nothing but the all those elements of the set capital X. So capital X contains n element. Okay, so this is nothing but the, if I consider the k is equal to 1, and this is this summation sign. For p1 we have n by p1. Okay, for p2 we have, okay, for e1 actually we have n by p1, for e2 we have n by p2, something like that. Okay, this is this. So taking n common, if I take n common, and this expression can be written in this way. This is very easy to observe. Okay, so this is one exercise example we have discussed. So the concept is very beautiful. If you feel any difficulty, so you can discuss with me. So you will try for this result already in a number theory. You can use this result. So this is a particular case. How can you find out this? Using the formula. Okay, so next we are going to discuss this. Thank you.